partial scan design. So, this was once used in the industry long before full scan design, and it became the dominant scan architecture, because as I was telling that there are some ad hoc design styles. So, some designers they found that if we put some of the flip flops onto on some access path, then it is easy to do the testing. So, as a result some partial scan architecture was staying there. So, that continued, and after this full scan came into picture, even then this partial scan in many cases they are used. They can be also be implemented using these masked D scan flip flops, clocked scan flip flops, or LSSD scan cells. So, that does not make any difference. Now, what happens is that some of the flip flops are converted, or some of the latches are converted into their scan counterpart. So, we can use combinational ATPG or sequential ATPG. So, combinational ATPG if we use, then of course, we are losing on the fault coverage, because it may not be able to generate tests for the sequential for the portions which are driven by those flip flops or latches. But in many cases it is seen that many faults are can be tested by applying random patterns as well. So, the combinational patterns, the patterns dedicated for testing combinational faults, they may also become sufficient for testing these types of faults. So, that way many of them will get detected. So, or we can use a sequential ATPG, which is more complex for getting this this type of test patterns. So, this is a case where we have got a masked D scan, a masked D based partial scan design. So, here you see that we in the design we have got 3 flip flops FF1, 2 and 3. Out of them, this first flip flop and third flip flop. So, they are converted into additional they are converted into scan flip flops, whereas flip flop 2 is not converted into a scan flip flop. So, this is a this is some type of partial scan design. So, this flip flop SFF1 and SFF3 being on the scan flip flop. So, they are actually connected in the chain from SI to Q of this first flip flop to the SI of third flip flop, and then going to the Q to SO. So, that is possible, but flip flop 2 is left out. So, it is possible to reduce test generation complexity by splitting the single clock into 2 separate clocks, one for controlling all scan cells, the other for controlling all non-scan storage elements. So, this is actually a suggestion for these ATPG algorithms. So, what it says is that you divide the whole design into 2 parts. One part is having where we have got this scan clock driving the circuit, and another case the normal clock driving the circuit. So, as a result we get 2 different portions, or 2 different portions are triggered by those clocks, and as a we can have this test pattern generator generating faults, generating test pattern in the first case for the scan chain based scan flip flop based portion. So, there it is a normal combinational ATPG, and for other flip flop the normal clock. So, that becomes a sequential ATPG, but the amount of job given to the sequential ATPG is less, because only a portion of the circuit will be given to it. As a result, it may do a good job. So, however, there are problems, because now we have to, if there are 2 separate clocks, like in this particular case we have not shown 2 separate clocks, the same clock is given to both the all the flip flops, but if there is a separate clock, then this routing of that separate clock also is an issue. Like as I have already said, that this clock distribution in the for the chip itself is a problem. How do you distribute the clock? And but if you have got more number of clocks, then the distribution becomes more complex. Now, the question is that in my design there may be a number of flip flops or number of latches. Now, how do you select those sequential element that must be put onto scan cell or that must be converted into scan cells? So, first approach is to have a functional partitioning approach. So, a circuit is composed of a data path portion and a control portion. So, data path portion is actually doing all the computations, like there are registers, multipliers, multiplexers, adders, subtractors, so like that. So, they are actually forming the data path. Now, for controlling this data path, we need to activate several signals, like first maybe the flip flops, first the registers will get the value from the outside world, then in that may be done in the first clock cycle. In the second clock cycle, maybe the adder will do the addition, taking the values from some registers and then writing the result back onto another register. So, that way those for this input registers, I need to enable I need to make their enable line high, so that the values are available, and for the destination register I must have the load signal given to it. So, and for the adder module I need to give the add signal. So, these are done by the control part. So, what happens is that the storage elements on the data path, they are left out of the scan cell replacement process, because data path flip flops, they normally form registers. Okay. So, those registers are not that much necessary to test, but the control path the flip flops, they are actually forming the finite state machine. So, that part needs to be tested, and this control part will actually excite the data path. So, in some sense I can say that if I have this control part flip flop setting easy, then the test pattern generation may become simpler. So, that is why the storage elements of the control path may be replaced by scan cells, whereas storage elements on the data path they are not put on a scan cell, because they are we do not want to put some values, because ultimately from the system primary input the values will be coming, and in fact any digital design if you look into, so it is like this. If this is the system boundary, so we have got the inputs coming from the outside world, and at the first stage there will be registers which will be holding these values. Then after that, after these values have been obtained onto the register, then there will be some combinational logic which will do some computation based on these values, and then these values of these outputs of this combinational logic, they will again be stored into some registers, and again these values are used by another combinational logic for the next stage of computation ultimately. So, there is another register here, and these register values are available as output. So, that is why these data path registers, so they are normally getting controlled by the primary inputs coming from the outside world. On the other hand, for controlling all these registers, combinational logic, etc., the control part, so it is implemented in by means of some FSM, so that at various states it controls the data path elements. So, I may need to test for a particular functionality. As a result, I need to put this FSM in a particular state for doing that fault excitation. So, for that purpose, it is easy if the corresponding flip flops can be accessed very easily, and that will help us in the testing process. So, storage elements on the control path, so they are replaced by scan cells. Storage elements on the data path, so they may not be replaced, they may not be used for that part. Second point is that a pipelined or feed forward partial scan design approach. So, it says that sequential circuit is make the sequential circuit feedback free by selecting the storage elements to break all sequential feedback loops. Like if we find that there is a flip flop here, and its D input Q output. So, this Q output is feeding some combinational logic, and this combinational logic output is again feeding the D. So, in this case it becomes difficult to control this particular flip flop, because to set this flip flop to some value, I need to set this combinational logic to some value, combinational logic inputs to some value, and for making the combinational logic to get a proper output for Q, I again need to set this Q value to some value. So, that way it becomes a circular logic, it becomes a circular logic. So, that has to be avoided. So, it creates a loop in the reasoning process. So, this has to be avoided. So, whenever we have got a sequential circuit, so we want to make it feedback free by selecting the storage elements to break the feedback loops. So, for that purpose one structure graph is constructed for the sequential circuit. We will see how to do this thing. third approach is a balanced partial scan design approach. So, we use a target sequential depth to simplify the test generation process for pipelined or feed forward partial scan design. So, we say that we will define the sequential depth essentially after so how many flip flops you are seeing in the path. So, if you may tolerate up to certain number of flip flops in a path, and after that we want to break that path. So, that is the balanced design style. So, we will see them. So, this structure graph, so a feedback free sequential circuit. So, that is what we are looking for. So, for that purpose we use a first of all we construct a directed acyclic graph. The maximum level in the structure graph is referred to the sequential depth. I think there is an example. Yeah. So, here you see that suppose this is a sequential circuit. So, where we have got these flip flops FF1, FF2 feeding this combinational logic C1. Similarly, this C2 is fed by FF1 and FF2, C1 is generating output for FF3. So, this way it is occurring. Now, if you consider these flip flops and then see like which flip flop can affect which one. So, each node of this structure graph, so it is corresponding to one flip flop. So, flip flop 1 node 1, flip flop 2 node 2, like this. Now, you see there is no dependency between flip flop 1 and 2. So, there is no edge between them, but flip flop 1 may affect flip flop 3 via combinational logic 1. So, there is an edge in the graph from flip flop 1 from node 1 to node 3. Similarly, from node 1 to node 4, so there is an edge because through C2 it can control it. From 2 to 4 also is there. Again, from flip flop 5 is controlling nobody. So, it is just taken like this. So, if we consider the sequential depth, so sequential depth is 3 in this case because there are maximum 3 levels, okay, in this graph. Okay. So, this is a directed acyclic graph. So, if you levelize, so this is level 1, level 2. So, 1 and 2 comes at level 1, 3 and 4 comes at level 2, and 5 comes at level 3. So, maximum depth is 3. So, the maximum level in the structure graph is referred to the sequential depth. A sequential circuit, it may contains, so it will happen if the circuit is feedback free, the sequential circuit is feedback free. So, if you look into this diagram, there is nothing from some say from flip flop 3 feeding back to flip flop 1. So, this graph is also a directed acyclic graph. So, there is no cycle in this graph. So, other possibility is that a sequential circuit containing feedback loops. So, there may be feedback loops. So, in that case we will construct if there is a feedback loop like in the graph, then it becomes difficult. So, those flip flops we need to consider, and then we have to break those feedback loop by making them scan flip flops. Okay, like here, if there was an edge from say node 5 back to node 1, then we need to convert one of these flip flops to scan flip flops, so that it is treated as a scan input. So, this flip flop 5 in that case will vanish. So, if this flip flop 5 is, if there was an edge from flip flop 5 to flip flop 1 and flip flop 5 is converted into a scan flip flop, then naturally that edge will vanish. So, that way this circular paths can be avoided. So, when I have got a full scan design, so this is an interesting observation. So, the sequential depth of a full scan circuit is 0, because then no flip flop depends on the other, because everything is controlled by the scan input. So, everything is controllable, everything is observable. So, that full scan circuit, the sequential depth is 0. So, again coming back to the definition. So, sequential depth is equal to the maximum number of clock cycles that needs to be applied in order to control and observe values to and from all non-scan storage elements. So, this is actually if we want to say observe the value of this flip flop, then I have to take it to this output, then only because that is the primary output. So, I can see output at this point only. So, somehow I have to excite this C1 C3 in such a fashion that this flip flop 1's response propagates through this C1 flip flop 3 and C3 and comes to flip flop 5. So, whether that is possible or not, that is a different issue, but still because that will depend on other inputs that I have to set for C1 and C3. But if it is possible, even in that case it requires 3 clock cycles for this flip flop 1 value to come at the output of flip flop 5. So, the sequential depth is 3 in this case. Why partial scan design? So, it has got advantages like the silicon area overhead is less, because less number of flip flops are converted into scan flip flop, and performance degradation is also less, because for flip flops, so we are not putting any multiplexer before them. So, as a result, the if some flip flop is on the critical path, so their performance is not affected. Disadvantage can result in lower fault coverage, that is because we are not having control over all the flip flops. So, there naturally there will be fault coverage, there may be fault coverage problem. Test generation time may be longer, because now we many cases we have to use this sequential ATPG. So, when we are using this sequential ATPG, so the sequential ATPG algorithms, they take longer time to run. So, that will take more time, and the support for debug, diagnosis and failure analysis, so that is also less. So, it offers less support for debugging, diagnosis and failure analysis, because of the same reason that the entire circuit is not visible. Okay. So, the circuit flip flop content, many of the flip flops will continue to be normal flip flops. So, they are not visible at the output. Other strategy is random access scan. So, random access scan design. So, we want to access any of the flip flops at any order, like in a serial scan. What happens is, if you want to access a particular flip flop, you have to shift in the patterns through the serial input line of previous flip flop, previous scan flip flops, and then only it will come there. So, if a flip flop is at level k of the chain, then after k pulses, k clock pulses only, you will be able to set that flip flop to the desired value. Similarly, if a flip flop is say m step away from the scan output line, the output flip flop, then it will require m clock pulses to get the output of this get the cell to the output point. So, that sometimes create difficulty, because we are unable to access them randomly. So, so that requires more time. So, this random access design, this tells that I will be able to access any cell in any order. So, can control or observe individual scan cells without affecting others, and reduce test power. So, and this is another issue, that reduce test power dissipation. So, what happens is that if I have a chain, suppose I have got a 4 cell scan chain, and I have initialized it to say 0 0 0 0, fine, they are initially all 0, and there is a combinational logic which is being fed from this scan chain. Now, what I require is that for this particular cell, I want to make it 1. Now, if I want to make it 1, so I cannot do it directly in a normal scan. So, first I have to make this one and then give shift pulses, then I have to give another pulse, so that the pattern becomes 0 1 0 0, another pulse 0 0 1 0. Now, when this thing is happening, when these bits are changing like this, so it is always feeding this combinational logic. So, hardware is never idle. So, this combinational logic is never sitting idle. So, as soon as this pattern is changing from 0 0 0 0 to 1 0 0 0, it is doing some computation. Some of the gates are changing their logic values, though the calculation is meaningless for our purpose, but something will happen. Similarly, this one, from this pattern, when it changes to this pattern, again some other gates will get excited and some logic transformation will take place. So, this way, every time I shift a bit into this scan chain, the scan chain pattern changes, and as a result these bits will also change for the combinational logic input, and the combinational logic will do some transitions. So, and as and when they make the transition, it will consume power. And we know that for CMOS circuits, this power is consumed only when its output changes. The dynamic power is consumed only when its output changes. So, if the input does not change, output does not change. So, if the input is changing, then there is very high chance that the output will also change for different gates in the logic. So, if I am doing a serial scan, then at every time, at every shift, I am consuming some power, because that will go to the combinational logic, that input will go to the combinational logic. Whereas, in case of random access scan, so I am allowed to access a particular cell directly. So, in this diagram, So, I do not have to do serial shifting like this, I can directly access this cell and modify this value to 1. So, if that is possible, so previously the input was 0 0 0 0 for the combinational logic, now it is 0 0 1 0. So, number of transitions that the logic sees is much less. So, as a result the power consumption will also be less. So, this so that is why it says that it reduces the test power dissipation and simplify the process of performing delay test. So, what happens in case of delay test is that we need to measure the delay. So, first we apply one pattern and so that the output settles to some value, then we apply a second pattern to excite a particular gate, okay. So, that gate makes a transition and that transition gets transferred to the output, and the delay of this gate in making the transition, that gets reflected in the delay at the output at the primary output of the circuit. So, this has to be so two patterns are to be applied. First one pattern for setting the value and the second one is for changing the value. So, these two patterns are necessary. Now, in a scan based environment, if I am trying to do this, first I apply a pattern, then I have to apply a totally new pattern. So, that means I have to again do lot of shifting for applying the second pattern. So, that is cumbersome. On the other hand, if I have got random access scan, then I can possibly change these bits directly, so that I can go to the second pattern very easily. So, it simplifies the process of performing the delay test. Disadvantage: high overhead in scan design and routing. So, now every scan cell has to be addressable. So, as a result I need to have a proper decoding of this scan address. So, it becomes a bit cumbersome, and routing, because now the scan cells are actually put onto the system by the designer. Okay. So, test engineer they cannot tell that I want the scan flip flop at this position or that position. So, that is done by the designer. Designer has put the flip flops from the design angle and they have put it as close as possible to the required portion. Now, later on when this test engineer come, so they have to design this scan cell, scan chain. So, they try to make as good a job as possible, but that may not be sufficient. This random access scan, so that may be putting them onto this two dimensional organization may be difficult. Then there is progressive random access scan. So, this traditional random access scan issues, so they are resolved to some extent in the progressive random access scan. So, this is the traditional random access scan architecture. So, as I was telling, the scan cells are arranged in a two dimensional array. Okay. So, so if there are n number of scan cells, then a log n bit address will be log n bit address shift register will be necessary, and then out of this log n bit, some of the bits will be given to the row decoder, some of the bits will be given to the column decoder. So, this address shift register, so this has got the cell address which we want to change, and then this is given, some part of it given to the row decoder, some part of it is given to the column decoder. So, they decode the values and then the appropriate scan cell will get selected by this, and the scan input whatever we are looking for, so that will be loaded into the corresponding scan cell. And similarly, we can also, if we want to read the content of a particular cell, so this scan out line, the content of that cell will be available on the scan out line. On the other hand, this progressive random access scan, so this is similar to say one static RAM type of design. In normal mode, so all horizontal row enable signals, that RE signals, are set to 0. So, all these RE signals are at 0. So, that each scan cell will act as a normal flip flop. So, these back to back inverters, so they are actually that flip flop that will be there, and this will force each scan cell to they will so if this RE line is 0, that means these transistors are off. So, this SD bar, both lines are off. So, they will not get selected. As a result, it will continue as normal D flip flops. But when in the test mode, the test response from D, to capture the test response from D, this RE signal is set to 0. So, and a pulse is applied to the clock. So, this RE signal is 0 and this clock pulse is applied. As a result, from the test pattern or test bit whatever you want to store, so that will come through this transmission gate and it will get latched onto this back to back inverters. In normal mode of operation, you see that this is driven by these clock signals, they are complement of each other. So, this phi is phi bar here and this phi is phi bar there. So, as a result we have got complemented signal. So, when this D is, when the clock is high, then only when this phi bar is high or the clock is low, then only this D can come into this thing. So, that way we can put this D value onto this flip flop. So, that is actually the capture operation. And similarly, when we are trying to read this design, read the content of a cell, then what we have to do is that we have to make this RE line high, and as we make RE line high, the content of this cell will be available in SD and SD bar lines. So, this is typical SRAM design. So, this is SD and SD bar. So, we can compute the difference between their voltage levels, and there are sense amplifiers and all that in normal SRAM organization. So, it is done exactly in that fashion. We will not go into that detail. So, rows are enabled in a, so the sense amplifiers are there. So, basically these column drivers and sense amplifiers are there. So, they will drive individual columns and sense amplifier will sense the difference between SD and SD bar line and see the difference. So, rows will be enabled in a fixed order, so that we can read all these scan cell elements, and it is only necessary to supply column address to specify which scan cell in an enabled row to access. So, they are so this is done in a sequential fashion. This row access is in sequential fashion by the column line address decoder. So, we can select a particular column, like which value we want there. So, that way that value will come to the combinational logic and that will be applied. Okay. So, this combinational logic has got n inputs. So, all these n inputs will be coming to this through this random access scan architecture. There are several scan design rules. So, we will continue with this in the next class.